Right. Okay. Good evening, all. We'll start. How about my audio and video? Is it clear enough? Okay. Good evening, all. Right. We'll start. How about my audio and video? Okay, it's fine now. Right. All right. We'll start. Right. Listen. Okay. So we'll be starting elasticity as planned today. Now, in our properties of matter, in lineup of properties of matter, we have finished surface tension and viscosity during the last month, and today I'm starting elasticity. That is the last part, last part actually in properties of matter, right? And during the month, so today we'll be doing elasticity, right? Elasticity, and the other main lesson to be covered during the month is, right? Main lesson to be covered during the month is matter and radiation. Matter and radiation, unit 11, right? Unit 11. This is a small part, right? So we'll be starting with this today, right? And this will be the main lesson to be covered during the month, unit 11, matter and radiation, right? So that's a monthly plan for February. Right? This will be our main lesson. Okay, so we'll start without further ado. Take down the heading as elasticity. Take down the heading as elasticity. Elasticity. Right, listen. So in physics, right? In physics, elasticity means, right? Elasticity means there is not only about stretching objects, right? But also contracting is there. Both ways, either way, it is called elastic, right? Either way, it is called elastic. So therefore, if there is any object which can change the shape, with an applied force, that is called elastic, right? If it can change the shape with an applied force, that is called elastic, right? We call that a deformation. We call that a deformation. So this is a keyword. Deformation, right? Deformation is the word used to say that it is changing shape. Changing shape in the sense it can either be increasing length, maybe increasing volume, area, or decreasing length, volume, area, right? Anything. If there is a changing shape, that is called deformation, right? Elasticity is the study on deformation of objects. Got it? Elasticity is the study on deformation of objects, right? Which means when we apply forces, now as an example, consider this marker, right? When we apply forces, always from the molecular level, this gets deformed, right? So in some cases, that is very much visible to our own eyes, right? But in some cases, that is not visible to the eye, right? Now, for a pen like this, now even if I apply a force, it is not that visible how this deforms, but it deforms, right? Now, when we apply a force like this, it deforms, right? It deforms from the molecular level, but that is not visible. That's the thing. That is not visible. That is from a very minor level. But if we consider something like a polythene, right? When I apply a force, usually we can see how it extends, stretched in the polythene material, deformation. And if you consider something like a rubber band, let's say, when you apply a force, it gets stretched. That is very much visible, right? Everything is deformation. And in the world, there are no objects we don't have any kind of a deformation. All and I mean, each and every object deforms. Sometimes you won't see it. That's the only thing. Because now if this deforms by say 0.001 millimeters, that is not visible to our eye. That's the thing. Otherwise, all the objects, right, each and every object in the world deforms. Right. So as the first point, write down, first point below the heading, write down the study on the study on the study on the study on deformation of objects. The study on deformation. The study on deformation of objects. The study on deformation of objects. The study on deformation of objects is elasticity. The study on deformation of objects is elasticity. The study on deformation of objects is elasticity. Right. Next point, second point, write down. Deformation is, next point, deformation is the phenomenon of changing shape. Deformation is the phenomenon of deformation is the phenomenon of deformation is the phenomenon of changing shape. Deformation is the phenomenon of changing shape of an object. Changing shape of an object when a force is applied. When a force is applied. When a force is applied. Right. Listen. Now, when it comes to objects, they have their own limits of deformation, which means, right, I can't deform this as much as I like, right, or as much as I wish. We can't do it, right? At some point, it will be fractured or ruptured or broken. It is going to break, right? So therefore, it has its own limits of deformation, right? Now, under this lesson, elasticity, we will be mainly focusing on the limits of deformation, right? It has limits. Don't write, just look at the board. For deformation of objects, it has limits. Limits of deformation, right? To determine these limits, right, we have something here called modulus, right? To determine limits, we have modulus. So based on modulus, right, that's a value. Modulus is a value. So based on the value of the modulus and the concept behind this, we can decide whether up to which limit it can be deformed, up to which limit it can be stretched, or up to which limit it can be contracted, right? That is based on the modulus, right? Okay, then as a next point, write down limits of deformation of objects. Limits of deformation of objects. Limits of deformation of objects. Limits of deformation of objects are determined using modulus. Are determined using modulus. Are determined using modulus. Right. Next point. There are three main modulus types, three main moduli types. Plural of modulus is moduli, right? Plural of modulus is moduli, right? Right. There are three main moduli types. There are three main moduli types. there are three main moduli types based on the type of object. 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 Okay, look at here. So basically, we have three types of objects, three categories of objects here in elasticity, right? First one is linear objects. Don't write, look at here. First one is linear objects. Linear objects means wires, right? Rods, strings, right? Those are the linear objects. For linear objects, we have something called Young's modulus, right? So don't worry about these words. You will see everything in the coming part. Young's modulus, right? Now, by the end of today, we'll cover all the theory parts here in elasticity, right? And if time permits, I'll be starting all the applications today itself, right? Linear objects. And then for non-linear objects, non-linear in the sense, right? Non-linear in the sense, don't write. For non-linear objects, non-linear means they can either be 2D or 3D, right? 2D or 3D, two-dimensional objects or three-dimensional objects, right? Two-dimensional ones are like plates, discs, lamina, right? They are two-dimensional. 3D ones are all volumetric ones, right? All volumetric ones, right? For that, we have something called modulus of rigidity. Modulus of rigidity. Modulus of rigidity, right? And then the last one is for any object, right? For any object. For any object, right? Any in the sense, now there are some objects with which they don't have a distinct shape. No. Now, as an example, a liquid doesn't have a shape, right? A liquid doesn't have a shape, right? So likewise, there are some specific scenarios where we don't have a distinct shape for the object, right? So in such cases, and this covers everything, right? But for linear ones specifically, we have Young's modulus. For non-linear 2D and 3D ones specifically, we have this. And for all other objects which are not on these two, right? I mean, for the objects, these two cannot be used, right? This is applicable for any object. For any object, any in the sense, right? For any solid or liquid, right? Solid or liquid, especially when it doesn't have any shape, right? When it doesn't have any shape, right? Even rarely for gases also this is applicable. This is called bulk modulus. This is called bulk modulus. Bulk modulus, right? Now here onwards, listen, here onwards, this lesson is all about these three moduli, right? And calculations we have is only from Young's modulus. And we have all three moduli, right? But when it comes to calculations, we have only Young's modulus for A-level physics, right? Now, take down this. Yes, can do. It covers all, right? Take this down, this part. Take it down. Linear, non-linear, and any. So we are at the end of 26th week before the exam, right? So we are at the end of 26th week before the exam. 26th week. Right? So exactly you got 26 weeks and 1 day for the exam. Right? So starting next week, you got only 25 weeks. Just 25 weeks. Okay, finished? So write down below with a red pen. Write down below with a red pen. Put an asterisk mark and write down. Put an asterisk mark and write down. Put an asterisk mark and write down. Write down below with a red pen. Any moduli is written as the ratio between any moduli is written as the ratio between stress and strain. Any moduli is written as the ratio between stress and strain. Any moduli is written as the ratio between stress and strain. Right? Write down below again. Modulus equals stress over strain, and square O, highlight this. Okay, right. Now, as the next heading, write down stress. Next heading, stress. Right. So this is not the stress we have, right? This is not the stress we have. This is the stress the objects have, right? Stress. Okay, listen. Look at the board. Any stress is defined as, don't write. Look at the board. There are different types of stresses, right? Any stress is defined as force over perpendicular area, right? Any stress is defined as force over perpendicular area, right? Force over perpendicular area. When we say force over perpendicular area, we have another very popular quantity we know from this force over perpendicular area. That is pressure, no? So same thing in the sense stress has same units and dimensions as pressure, but we don't say it's a pressure because of some other different reasons which are coming up, right? Otherwise, as a unit and a dimension, it is same, right? Write this down and highlight this equation. Stress, force over perpendicular area. Right? So we write this as an equation, we write this as stress equals F/A. Right. So quickly, find units and dimensions of stress. Quickly, find units and dimensions of stress. Find units and dimensions of stress. Same as pressure, no? So units will be, right? Units will be units of F over units of A, right? N over M squared, that is Nm minus 2, right? And dimensions are dimensions of force over dimensions of area. Dimensions of force is mLT minus 2 over area L squared. that is ml minus 1 t minus 2, right? Write down below with a red pen. Write down below with a red pen. Any stress has any stress has same units and dimensions. Any stress has same units and dimensions of pressure. Any stress has same units and dimensions of pressure. Any stress has same units and dimensions of pressure, right? Same units and dimensions of pressure. Any stress has same units and dimensions of pressure. Right. Next heading, write down strain. Strain. Listen. Strain is defined as extension over initial length. Extension over initial length, right? Therefore, strain is written as E over L, extension over initial length. Extension over initial length, right? Now, when we say extension, right, from springs also you know, right? When we say a extension, right, that is not only about extension in physics, right? For both extensions and contractions, commonly we use extensions, right? Take it down. Take it down. And find units and dimensions of strain. And find units and dimensions of strain. Units and dimensions of strain. Find units and dimensions of strain. Units and dimensions of strain. Units. Extension is a length, right? Meters, right? Measured in meters. So let me write this way. Units of E over units of L, right? Extension is length, meters. Initial length is meters, right? So this is dimensionless, right? One means dimensionless, sorry, unitless, right? Then strain, units of E over, sorry, dimensions of E over dimensions of L, right? Dimensions of E is L, dimensions of L is also L, right? It becomes 1. 1 means that is also dimensionless, right? Write down below with a red pen, right? Mention below with a red pen, put an asterisk mark and write any strain is unitless and dimensionless. 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 Unitless and dimensionless. Okay, let's go on. Right. Now, when it comes to stresses, strains, based on the 3 object types I explained, right? So, based on the 3 object categories, types I explained, there were 3 modules I know. So, based on those types, right, there are specific types of stresses and strains. Right now, this part, what you are going to see is the different types of stresses and strains we have, right? So, as the next heading, write down tensile stress. Tensile stress. Tensile stress. Tensile stress. Look at the board. Look at the board. If a force is applied, look at the board. If a force is applied for an object, if a force is applied for an object parallel to its length, right, can be either way like this. If a force is applied parallel to length, right, if a force is applied parallel to length, such forces are called tensile forces. These forces are called tensile forces, right? Now specifically this is called tensile tension, right? Tensions, no, see, in the opposite directions. So this is called tensile tension, right? And this is called tensile thrust. Tensile tensions and tensile thrusts. Tensile tensions and tensile thrusts, right? So either way, if the force is applied parallel to length, right? The keyword is parallel to length. If the force is applied parallel to length, like this or like this, they are called tensile forces, right? Stress due to a tensile force, stress due to a tensile force is called tensile stress, right? Okay, first take this down. Take it down. Right? Can I explain again? Tensile forces are the forces applied parallel to length. Parallel to length. Right? Or in other words, we can say perpendicular to area. Parallel to length and perpendicular to area. Right? They are called tensile forces. Right? Either way, they can act as tensile tensions or tensile thrusts. Okay, write down below. Write down below. Forces applied parallel to length. Write down below. Forces applied parallel to length. 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 Forces applied parallel to length are called tensile forces. Forces applied parallel to length are called tensile forces. Right? Now, tensile stress is defined like this. Get here. Now, based on the general equation of stress, we are developing these ones. So, tensile stress is tensile force, right? This is tensile force over perpendicular area. Tensile force over perpendicular area, right? Tensile stress. This is equal to F over A as usual, right? But F is specifically a tensile force, right? Take it down. Take it down. Right now, we are going to define tensile stress. Listen, we are going to define tensile stress. We know if dimensions are different in numerator and denominator, we always define the quantity as unit terms, right? Now, this perpendicular area is then it is at the denominator, so it should be considered as a unit term, right? So this is a tensile force per unit perpendicular area, right? Tensile force per unit perpendicular area. right? Write down below in red. Write down below in red. In red, write down tensile force per tensile force per tensile force per tensile force per unit perpendicular area. Tensile force per unit perpendicular area. Tensile force per unit perpendicular area. Tensile force per unit perpendicular area is defined as tensile stress. Is defined as tensile stress. Is defined as tensile stress. Right? Next point, keep using red. Next point, keep using red. Perpendicular area should be considered. Perpendicular area should be considered. Perpendicular area should be considered without holes in the object. Without holes in the object. Without holes in the object. Right. Let's move on. As an experiment, write down tensile strain. Tensile strain. Tensile strain. Okay. Look at here. Look at here. Now, due to a tensile force we applied, right? Due to a tensile force we applied, say this object is either stretched or got contracted like this due to a tensile force we applied. Let me draw this in two diagrams. See, now due to a tensile force applied on this, right? See, say this object was extended or contracted, right? Let's assume the initial length as L. Initial length. Now here also initial length is L, right? And this change part of the length, is called extension, right? Either way it is called extension. Even though it is a contraction, that is also called an extension, right? That is also called an extension. Now we know strain is extension over initial length, no? E over L, no? So this is E over L, and tensile strain is the strain due to a tensile force, right? Tensile strain is a strain due to a tensile force, right? Strain is E over L, where E is extension. Extension can be either an elongation or stretch, right? Extension or a contraction, both. Either way, we call it a extension as a common term, right? Take it down. Take it down. Take down both of them and write strain equals E over L. Strain in the sense tensile strain, sorry. Tensile strain equals E over L. Tensile strain equals E over L. The word tensile refers to parallel to length. The word tensile refers to parallel to length. Write down below with a red pen. Right, again we are going to write the definition. Write down in red, write down extension per unit initial length. 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 Due to tensile force. Due to tensile force. Due to tensile force. Due to tensile force. Is defined as tensile strain. Is defined as tensile strain. Is defined as tensile strain. Okay. As a next heading, next topic, write down definition of Young's modulus. Definition of Young's modulus. Definition of Young's modulus. Definition of Young's modulus. Right. So at the board. So initially I told you, right? Initially at the very beginning I told you any modulus is defined as stress over strain. No? Any type of modulus is defined as stress over strain. Young's modulus is defined as, right? It is breaking down from that, right? So Young's modulus is defined as tensile stress over tensile strain. Tensile stress over tensile strain, right? That is how Young's modulus is defined. That's why Young's modulus is only applicable for linear objects, because tensile forces, parallel to length forces, can be applied only on linear objects. So that's why, right? That's why Young's modulus is applicable only with linear objects. Right now, I think those dots are connected, right? So write down definition of Young's modulus. Write down this. Young's modulus equals tensile stress over tensile strain. Right now, let's write the equation as well. Young's modulus is denoted by Y, tensile stress F over A, right, over tensile strain E over L. Okay, write down this way. For L, you can use either simple L or capital L, that doesn't matter. Okay, now we are going to define this. Listen, we are to define this. Right. So this is, right, definitions of modulus, right? There's a small different thing from our standard procedure, standard manner we do in physics about a definition, right? Now, even though this has different units and dimensions in numerator and denominator, right, this is defined as a ratio. So that's a special case. Keep that in mind separately. This is defined as a ratio, right? This is a definition. Definition is questionable, right? Usually with the essay questions, it is asked. Write down the definition in red. Write down the definition in red with an asterisk mark. Write down the definition in red. Write down the ratio between tensile stress, the ratio between tensile stress, the ratio between tensile stress and tensile strain up to a certain limit, up to a certain limit, up to a certain limit, up to a certain limit is defined as, up to a certain limit is defined as, up to a certain limit is defined as Young's modulus. Up to a certain limit is defined as Young's modulus. Up to a certain limit is defined as Young's modulus. Is defined as Young's modulus. Right? Okay, now from this equation, see, we are going to get the final equation of Young's modulus. So y equals f over a over e over L, right? So we usually keep the equation subject in f over a, right? F over a equals y times e over L, right? This is how we keep this equation usually. Write it down this way and highlight this equation. Highlight this equation. Highlight this equation. Right? Write down. Understand these fundamental theories to the fullest, right? Elasticity is also a smaller and an easier part we have. Right? So let's define terms. Let's define introduce terms. F, introduce them. That is not a force, that is tensile force. F, define tensile force. Then A, no marks if you say area, that is perpendicular area. F, tensile force. A, perpendicular area. Perpendicular area. Perpendicular area. Put a curl bracket for these two. Put a curl bracket for these two. And for F over A, introduce a single term. For F over A, tensile, what? Tensile stress. Right? For F over A, write down tensile stress. F over A, tensile stress. Right? Then E. What is E? Extension. E, extension. L, initial length. L, initial length. And put a curl bracket for these two and write E over L and introduce E over L as tensile strain. As tensile strain. Right? Last but not least, introduce Y as Young's modulus. Y, Young's modulus. Young's modulus. Right. Find units and dimensions of Young's modulus. Find units and dimensions of Young's modulus. Quickly. Find units and dimensions of Young's modulus. Units and dimensions of Young's modulus. Find units and dimensions of Young's modulus. Units will be same as before. Nm minus 2. Dimensions will be same as before. Ml minus 1, T minus 2. Right? I told you initially also. Any modulus is written as stress over strain. No? So any modulus has same units and dimensions of pressure. right? So any modulus, not only Young's modulus, any modulus has same. Write it down. L, initial length. L is initial length. Put your questions to the main chat. Put your things to the main chat. Right? Write down below with a red pen again. Right? For the last time we are writing this. With a red pen, put an asterisk mark and write down units and dimensions of, write down units and dimensions of, units and dimensions of any modulus. Units and dimensions of any modulus. Units and dimensions of any modulus. Any modulus. Any modulus. Comma, any stress. Units and dimensions of any modulus, comma, any stress. Any stress are equal to that of pressure, are equal to that of pressure, are equal to that of pressure. Right. Listen, another important idea. Listen, deformation was changing shape, right? Changing shape. Now, when it comes to tensile forces, we had tensile stresses and the extensions, they are linear, right? Linear extension, linear ones, right? From thermal physics, we know, by heating or cooling an object also, shape can be changed, no? Isn't it? Because of the expansions, we can change the shape of an object by heating or cooling. Now, as an example, if this linear object is heated, this elongates, this extends. If this is cooled, this contracts, shorten the length, right? Now, we can link that same idea to here as well. See how it is done. See, if this extension is due to a temperature difference, right? So when I say the extension is due to temperature difference, that is all about linear expansion. Thermal physics, right? See, if extension, don't write, look at the board, is due to a temperature difference, right? Now, let's say due to a temperature difference, this original length L was increased to this, right? Now, this has to be E, no? This has to be E, right? E. But we know from linear expansion, see, by linear expansion, don't write, look at here. By linear expansion, we know, right? This same extension can be written as delta L. In our linear expansion, change of length, right? Change of length, that is L1 alpha theta, no? L1 alpha theta, right? Which means now if I plug these values, E can be written as, if the initial length is L alpha theta, E equals L alpha theta. Since E equals L alpha theta, see what I'm trying to do? I'm going to plug that here in our Young's modulus equation. See? So we can plug that here in our Young's modulus equation. Now from this, then F over A equals Y times E over L. Now E is L alpha theta over L. L to L cancels, right? Then that is F over A equals Y alpha theta. F over A equals Y alpha theta. So this is the other form, right? This is the other form of the same equation, Young's modulus. by using temperature difference, or in terms of temperature difference by using linear expansion, right? Another form of the same equation, right? Now start from here and take it down. Start from here and take it down. Start from here and take it down quickly. Also, how did you get changed? Thermal physics. Thermal. An equation coming from thermal physics. Unit 4. Did we derive? You have derived if you have done unit 4. Take it down quickly. Right? So introduce these new terms here. All other terms we have introduced before, no? Right? All other terms we have introduced before. Right? Introduce the other terms. F(y) is already introduced. Y is known. Introduce alpha and theta. Introduce alpha and theta. Alpha, coefficient of linear expansivity. Alpha, coefficient of linear expansivity. Coefficient of linear expansivity. Coefficient of linear expansivity. Coefficient of linear expansivity. Theta, temperature difference. Theta, temperature difference. Theta, temperature difference. Temperature difference. Right. So we are going to move on. So you better separate this with a horizontal line. Separate this with a horizontal line, and as the next topic, write down shear stress. Separate this with a horizontal line and write down shear stress. Shear. Shear stress. Shear stress. Listen. Okay, before moving on, raise your hand if everything is clear up to this point. So if not, if any doubts, you can ask and get it clarified. Quickly. 2, only 2, 4, 5. So if any questions, ask and get it clarified before moving on. Right? Even if you are on YouTube, put it to the live chat and get it clarified. Unit extension was due to tensile force. In linear expansion also, the forces are all tensile, right? Coming from thermal. All forces in linear expansions are tensile. What else? Any other questions? Anything else? Right. Okay, then if no questions, let's move on. Shear stress. Okay, look at here. Shear forces means, don't write, don't draw. Just look at here. Shear forces means if we apply a force parallel to area. If we apply a force parallel to area. Now let's say we are applying a force on this parallel to this area like this. Right? Such forces are called shear forces. Now as an example, right, consider this. Now, if we can apply a force parallel to this area like this, see, it also deforms this, but the type of the force and the application of the force is different from that linear ones, right? Parallel to area, such forces are called shear forces, right? Stress due to a shear force is the shear stress, right? Shear stress. Write down below. Sorry, before writing down, take this down. Take down the diagram. Shear. Okay, write down below. Forces applied. Forces applied. Forces applied. Forces applied parallel to area. Forces applied parallel to area. Forces applied parallel to area of an object. Forces applied parallel to area of an object. Forces applied parallel to area of an object are called shear forces. Are called shear forces. Are called shear forces. Are called shear forces. Right? Are called shear forces. These things are very comparative. Shear stress is shear force. This is shear force over perpendicular area. Right? Shear force over perpendicular area. Right? Very much comparative. Right? Write down. Shear stress. Shear stress equals shear force over perpendicular area. Right. So we are going to define this same way, exact same way. Define with a red pen. Define with a red pen. Right. Define with a red pen. Very much similar to the previous one. Write down shear force per. Shear force per. Shear force per. Shear force per unit perpendicular area. Shear force per unit perpendicular area. Shear force per unit perpendicular area. Shear force per unit perpendicular area is defined as shear stress. Is defined as shear stress. Next heading, shear strain. Shear strain. Okay, look at here. Look at here. When shear forces are applied, look at here. When shear forces are applied, right, the object is going to deform like this. Not an elongation, but it deforms like this with the shear force. Right? When shear forces are applied, This is how the object deforms. Now initially this side was vertical like this, and now with this force, because we are applying this force parallel to area now, right? So it measures this area, right, or slides the area in this particular direction. So in the molecular level, these layers are sliding towards a particular direction. So because of that, it deforms this way. It deforms this way, right? Now we know this is due to due to this force, due to this force, right? Right. Now to measure this easily, we are going to measure this angle. To measure this easily, we are going to measure this angle. So we know stress is extension over initial length. No? Any stress is extension over initial length. Now this is, sorry, any strain is extension over initial length. Now about the shear strain, right? About the shear strain, that is also E over L, that is true, right? But we consider E as this relative displacement of one point, and initial length as this initial length, right, perpendicular to the extension. Therefore, using the diagram, we can easily write this as tan theta as E over L, right? Tan theta as E over L, right? So this equals tan theta, right? So therefore, shear strain is defined as tan theta, because it is not practical to measure E and L here, but measuring angle is very much practical, right? Make a angle with the make a slide with the angle like measure කරන්න පුළුවන්. We can measure the angle, but can we measure this length practically? No, right? We can't measure this length practically. Since we can't measure this length practically, right? Instead of that, we are using the angle. One comparative scenario for this is in optics. In optics, we usually have linear magnifications, no? But since for optical instruments, linear magnification cannot be measured because we use object heights, object distances, image heights, image distances cannot be measured. So instead of that, we are measuring an angle as angular magnification. Very much similar idea. Since these lengths cannot be measured, angle is measured. So shear strain is defined as tan theta. Right? Take it down. Take it down. So wouldn't E change at different points as you go down? But angle doesn't change. That's why angle is measured. Right? Doesn't matter. If E changes, then according to E, L changes, no? Tan theta remains same. Tan theta remains same. Right? Because either way, it creates the same triangle like this. Tan theta is same. Why the box goes sideways? Because of the parallel force. Because of the parallel force. Parallel to area. The force is parallel to area. If the force is parallel to area, then that surface is trying to slide. Only the surface. When the surface is trying to slide, it goes sideways. Take it down. What about the first box? It goes. I haven't drawn. So if needed, you can draw the second scenario. In the second scenario, this will be like this. Right. Write down below with a red pen. Right. First, write down the definition. Definition in red. Extension per. Write down in red. Extension per unit initial length, extension per unit initial length, extension per unit initial length due to a shear force, extension per unit initial length due to a shear force, due to a shear force, extension per unit initial length due to a shear force is defined as shear strain, is defined as shear strain, is defined as shear strain, right? Is defined as shear strain. As another point with an asterisk mark, write down, as another point with an asterisk mark, write down relative displacement, relative displacement, relative displacement among layers, relative displacement among layers, relative displacement among layers of molecules, relative displacement among layers of molecules, relative displacement among layers of molecules is considered as is considered as extension due to a shear force, is considered as extension due to a shear force, is considered as extension due to a shear force, is considered as extension due to a shear force. Right, next point, keep using red. The changed angle is measured, the changed angle is measured, the changed angle is measured, the changed angle is measured the changed angle is measured with the practicability, with the practicability, with the practicability. The changed angle is measured with the practicability. Right. Next heading, definition of modulus of rigidity. Next heading, definition of modulus of rigidity. Definition of modulus of rigidity. Right. So we know any modulus is stress over strain, no? Same idea. Modulus of rigidity is shear stress over shear strain. Shear stress over shear strain. Right. So modulus of rigidity is denoted by K. Modulus of rigidity is denoted by K. Shear stress is FOA, right? But shear strain is tan theta. Shear strain is tan theta, right? So this is how the equation of modulus of rigidity derives, right? Okay, take it down, starting from here. Can you tell the first point again? I can't remember now. Can anyone put it in the chat? I can't remember in exact words I gave. Right? Can anyone put it in the chat, please? Take it down. Thanks, Umaima. Thanks. Right, take it down. Finished. So we are going to define this again. We are going to define this. Write the definition in red. Write the definition in red. Write the definition in red. The ratio between, write the definition in red. The ratio between shear stress and shear strain. The ratio between shear stress and shear strain. The ratio between shear stress and shear strain. The ratio between shear stress and shear strain is defined as the ratio between shear stress and shear strain is defined as modulus of rigidity. Is defined as modulus of rigidity. Right? Okay, as another point write down, keep using red. Modulus of rigidity is applicable. Write down. Modulus of rigidity is applicable. Modulus of rigidity is applicable. Modulus of rigidity is applicable. Modulus of rigidity is applicable for any object. Modulus of rigidity is applicable for any object except modulus of rigidity is applicable for any object except linear objects. Modulus of rigidity is applicable for any object except linear objects. Right? Okay, now again, you can separate this with a horizontal line. Right? Separate that with the horizontal line, and as an next heading write down bulk stress. Next heading, bulk stress. Bulk stress. Bulk stress. Listen now. Listen. Bulk stress and bulk modulus is for any object, no? So therefore, it is specifically for any shape of an object. For any shape, right? Even if that doesn't have a shape, we can apply this, right? So therefore, we are considering a random shape like this, right? We are considering a random shape like this. We know any stress is force over perpendicular area. Any stress is force over perpendicular area. But here, now we can't get the perpendicular area at once. This is a random shape, any shape. Right? It can be any shape, either gases or liquids, anything. Right? Solids vallat puluwan. This is for anything. Therefore, now since we can't write the perpendicular area, we can't get the perpendicular area at once. Right? But we know force over area can also be expressed as a pressure, no? Right? Force over area can also be expressed as a pressure. But for pressure, if we consider pressure at once, right? Pressure at once, we don't need to consider the perpendicular area from point to point or surface to surface like one to one. So therefore, we are taking this idea a little bit forward now, right? Stress is force over area, but force over area is also pressure. Force over area is also pressure, right? So therefore, let's consider the pressure applied on this object as P. Let's consider the pressure applied on this object as P, right? So with this pressure, right? With this pressure, let's assume the initial volume of the object as initial volume. This is for any object, no? So let's assume the initial volume as V1. Initial volume as V1, right? Now with this pressure, we know this volume is going to decrease, contract, right? Then after being contracted, let's say it contracts to this level and this new volume is V2, and let's consider this change of volume, let's consider this change of volume as delta V, right? Let's consider this change of volume as delta V, right? So kind of comparative with volume expansion in thermal, right? Okay, first take this down, take this down, take this down, and for the equation, I'll be writing the equation properly here. So we are to write bulk stress, right? Bulk stress should be bulk force over perpendicular area, right? But it is not practical, perpendicular area, but it is not practical to get perpendicular area of an irregular shape, right? It is not practical to get the perpendicular area of the irregular shape. So therefore, instead of F of A, at once we are going to consider pressure, right? Consider it as pressure. Take down. Take it down. Can you explain again? Take it down. I'll explain again before moving on. Now, as an example, let's consider this object. As an example, let's consider this object. There is a clock. It's a clock, right? Now consider this object, right? This don't have, right? This doesn't have any regular shape. This is not a regular shape. So is there any possible way that we can determine, we can identify all the perpendicular area here? No, right? This can be in any shape. This can be in any shape. So there's no proper way to identify the perpendicular area or determine the perpendicular area. But when we consider pressures, right? When we consider pressures, we know for pressure, if we consider pressure as an overall, that doesn't matter, because pressure acting on any point is same if that is on the same atmosphere, right? Pressures are same. So therefore, if that pressure is considered at once as P, so with this pressure we know this volume expands. Volume either expands or contracts. Now in this case, I have drawn a contraction like this, right? Because of the pressure, then no need to check force and area point to point. Then as an overall, we can consider total pressure as P, right? Then when volume contracts, I have considered the initial volume as V1 and final volume as V2. The change of volume now is delta V. Change of volume now is delta V, right? Okay, write down below with a red pen. Now we are to define this. We are going to define this bulk stress. Write down the definition in red. Write down the definition in red. Write down increase in pressure. Write down increase in pressure. 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 Increase in pressure due to a bulk force. 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 Increase in pressure due to a bulk force is defined as increase in pressure due to a bulk force is defined as bulk stress. 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 Right. Next heading, bulk strain. Bulk strain. Bulk strain. Right. Look at the word. Bulk strain. So we know any strain was defined as E over L. No? Any strain was defined as E over L. Listen. Any strain was defined as E over L. Extension over initial length. Extension over initial length. But now, if we get an irregular shape like this, is there any surface or any point that we can measure extension? A linear one? No. Right? So we don't have any other surface where we can measure the initial length as well, because this can be any irregular shape. So therefore, when it comes to bulk stress, this idea of E over L is again taken to another step forward. Right? These are ratio between, these are ratio between lengths and change of length and the initial length. No? Length, which means change in length over initial length. This is the ratio of the object between the change in length and the initial length. Right? So therefore, if we consider a volumetric object, a 3D object, an object of any shape, this ratio is same as the ratio between its volumes as well. This ratio is same as its ratio between volumes as well. So therefore, instead of E, we are going to consider delta V, change of volume. Instead of L, we are going to consider V1, initial volume, right? So therefore, this idea is taken forward as it is to match with this scenario, because we can't measure practically any lengths about this irregular shape. This is a 3-dimensional irregular shape. Lengths measure karanna bෑ. Right? So therefore, since the ratios are same, the same idea is taken to the next step as the ratio between volumes. Right? So therefore, bulk strain is defined as, don't write, look at here. Therefore, bulk strain is defined as delta V over V1. So about this we have discussed in volume expansions, right? What is a single term for this? Anyone who can remember? What is a single term for this? Delta V over V1. I discussed. What is a single term for this? Delta V over V1. We had another term for delta V over V1 in expansions. What is it? Anyone? For delta L over L1, delta A over A1, for delta V over V1, we had different terms. What was it? Anyone? Thermal expansion. What about the ones on YouTube? Anyone? We had a single term for this, delta V over V1. We had a single term for this. What was it? Yeah, it's gamma theta. It is correct. So what was gamma theta? What was the term? I use a term. It is gamma theta. You are correct. What was the term? The equation is gamma theta. What was the term? Starting from F. What was it? Starting from F. So it's correct. It is gamma theta. As an equation, right? So what did we find using gamma theta? So what was the term for that quantity? Starting from F. Too bad. Fractional difference in volume. Fractional difference. This is called the fractional difference. Fractional difference Gamma theta tamai, right? That is called the fractional difference as a term, right? That is fractional difference. So that is linked, huh? That is linked. This fractional difference, right? Keep that in mind as well. This is the fractional difference in volume. Fractional difference. So fractional change in volume. Fractional difference in volume. Okay, take it down. Take it down. And this is now, since this is not defined, let me define these two terms here itself. This is change in volume. Change in volume over this one is, right, over this one is initial volume. Okay, take it down. Bulk strain. Okay. Define this below. Define. Use a red pen. Use a definition. Use a red pen and define. Write down the ratio between. Write down the ratio between. The ratio between. The ratio between. The ratio between decrease in volume. The ratio between decrease in volume. The ratio between decrease in volume. Decrease in volume and initial volume. Decrease in volume and initial volume. Decrease in volume and initial volume due to an increase in pressure. 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 Due to an increase in pressure is defined as, due to an increase in pressure is defined as, due to an increase in pressure is defined as bulk strain. Due to increase in pressure is defined as bulk strain. Right. So when it comes to definitions, we do definitions only for increasing pressures, right? Only for the increasing pressures. That's why change of volume is written as decrease in volume instead, right? Because this is about an increase in pressure. For the definition, we use increasing sign. Otherwise, it's valid either way. All right. Then next heading, definition of bulk modulus. Definition of bulk modulus. Write down. Definition of bulk modulus. Definition of bulk modulus. Right. So we know again any modulus is stress over strain. Then bulk modulus is bulk stress over bulk strain. Right. Bulk modulus is written as B. Right. B. Bulk stress is a pressure now. So pressure over bulk strain. Bulk strain is delta V over V1. Delta V over V1. Right. So this is how the equation of bulk modulus derives. Take it down. There you go. Right, write down the definition in red. Same thing. Write down the ratio between same thing. Now we have done this two times before. The ratio between bulk stress and bulk strain. The ratio between bulk stress and bulk strain. The ratio between bulk stress and bulk strain. Bulk stress and bulk strain is defined as bulk modulus. The ratio between bulk stress and bulk strain is defined as bulk modulus. Is defined as bulk modulus. Bulk modulus. Okay. As another point, write down using red, right, with an asterisk mark, write down bulk modulus is applicable. Bulk modulus is applicable. Bulk modulus is applicable. Bulk modulus is applicable. Bulk modulus is applicable for any. Bulk modulus is applicable for any. Bulk modulus is applicable for any solid, comma, liquid, solid, comma, liquid, or gases, solid, comma, liquid, or gases, hence, since pressures and volumes, since pressures and volumes, since pressures and volumes, since pressures and volumes, since pressures and volumes are used, since pressures and volumes are used accordingly as measurable parameters, accordingly as measurable parameters, accordingly as measurable parameters, accordingly as measurable parameters. Right. So we are going to step into the core area here in elasticity. So before that, if there's anything to clarify, you can ask. Now the next part is the core area about elasticity. Simply the heart of elasticity is coming up, right? The core of elasticity is coming up, right? So before that, any questions up to this point? And raise your hand if everything is clear up to this point. If not, always you can raise your questions, raise your doubts. What about you? We can give a confirmation before moving on. Right. Can you please explain bulk stress? Bulk stress is simple as pressure, increase in pressure. Right. Bulk stress is increase in pressure. Right. Bulk stress is increase in pressure. Right. Pressure of any type of an object can be increased. No? For solids, liquids, and gases, increase in pressure is bulk stress. Increase in pressure. Right. Overall increase. Overall increase. Increase in pressure. Any other questions? Any other questions? For any solid, liquid, gases, we can write pressures. Right. So that's why pressures are used instead of forces when it comes to bulk modulus, as to be applicable, as it to be applicable for any shape and any material. That's why. Right. So if no any questions, we'll move on. As an next, write down ductile material. Ductile material. Ductile material. So I guess you have heard the word. I guess you have heard the word ductile in O levels. What is the meaning? What is a ductile material? What's the idea you have about a ductile material? Anyone? What is a ductile material? Anyone? Ductile material, ductile and brittle. I think you have come across these two, ductile materials and brittle materials in O levels. Can be broken into wires. Yes, I think in O levels some kind of an idea is given. Yeah, that's not the definition, but it's correct. I mean, to some extent that is correct. To some extent that is correct. Yeah, that is what I expected. O levels name, right? So even though it says something regarding wires in O levels, that is not the definition. Right now, today you are going to learn the exact definition of a ductile material, because now only you know, right? Now only you know about stress and strain. In O levels, you don't have stress and strain, no. So therefore, the correct definition of a ductile material cannot be given. That's the thing, right? Listen, don't write. Listen, ductile material is a material which can withstand for a considerably higher strain. Right? If the material can withstand for a considerably higher strain, what is strain? EOL. For higher strain, such materials are called ductile. What are the examples for ductile material? What are the examples for ductile materials, you know? What are the examples? Ability to stretch and bend. Examples for ductile materials. Copper, aluminium, any metal is correct. What else? Right? Otherwise, if we say copper, aluminium, like that, there are like hundreds of metals to be given. Any metal. What else? Is it only metal we have as ductile? Is it only metal? Anyone has different thoughts? Metals are correct. Metals are correct. What else? Now I told you the definition. If the material can withstand for a higher strain, right? Higher strain, that should be ductile, no? Plastic, yes, correct. What else? Plastic materials are correct. What else? And another popular one is polythene. Polythene is also correct, right? Because it deforms to a higher EOL, right? Rubber is also correct, right? Okay, let's move on. Write down below ductile material. Good. Let's move on. Write down below a material which can withstand for a material which can withstand for a material which can withstand a material which can withstand for a higher strain, stand for a higher strain, until they get ruptured, until they get ruptured, until they get ruptured. Rupture means breaking, huh? Rupture means breaking. Until they get ruptured, until they get ruptured, are called ductile material, are called ductile material, right? So write down few examples. Few examples are correct. Metals, right? Write down few examples. Metals, then rubber, polythene, plastic, right? Then next heading, brittle material, brittle, brittle material, brittle material, brittle material. Brittle is the exact opposite of this. Opposite in the sense, brittle materials don't have a higher strain. They have a very small strain, right? It's like almost no EOL, right? Almost zero EOL, almost no EOL, no strain, right? Such materials are called brittle. Any examples for brittle material? You know, any examples for brittle material? Any examples for brittles? Glass is brittle. So in others, why was it defined as can be broken into wires? Because you don't know the idea of stress and strain, right? So otherwise, it won't be a touch and go, right? In O levels, that's why it's just touching on the surface. Forming wires, again, forming wires in the sense that is the ability when stretching. Forming wires, the ability to form wires, not break into actually form wires. Because when tensile forces are applied, this is getting thinner and thinner, and it's forming wires. No, that's the whole idea. But it is not the exact idea when it comes to the definition, right? So forming wires is also it's doable, but it doesn't make that sense when it comes to the definition. Okay. Concrete, correct. What else? Good. Graphite, correct. Glass, yeah, correct. So there are more. Clay materials like bricks or what we call porcelain, ceramic, right? Anything. Okay. Write down. Write down. Write down. Any material which has, write down. Any material which has, sorry, which can withstand, any material which can withstand only for a small strain, only for a small strain, which can withstand only for a small strain, until get ruptured, until get ruptured, until get ruptured, until get ruptured, until get ruptured. until get ruptured are called brittle material, are called brittle material, are called brittle material. Right, are called brittle material. Right, so write down few examples. So all the examples you gave are correct. Write down few. Glass, write down few examples. Glass, clay, ceramic, porcelain, concrete, graphite slash carbon, graphite slash carbon, right? Okay, listen now. Right, let's move on. Next heading, write down variation between, write down variation between tensile force and variation between tensile force and extension, variation between tensile force and extension, variation between tensile force and extension of a ductile material, of a ductile within brackets write down elastic, of a ductile within brackets elastic, of a ductile within brackets elastic material, of a ductile within brackets elastic material, variation between tensile force and extension. Right, listen now, listen carefully, right? This graph is, now we are going to plot a graph. This graph is a result of an experiment, right? Experimental result, right? We also can do the experiment in labs, right? And we have it in our practical guide as well. So this graph is the result of that experiment, right? So that is how I'm going to draw this graph. And here we are going to explain the reasons for the shape of this graph, right? That's the thing. Otherwise, plotting the graph is done through an experiment. Right? So here, if we plot this graph between F and E after the experiment, this is what you are getting. First part is linear, right? First part is linear, and then it deviates from the linearity and goes somewhere here like this, right? You are getting this type of a graph. Something like this, right? And here we can identify few special points in the graph, right? Few special points on the graph like this, right? And between each point, let's say this is O, A, B, C, D, and E, right? So between each 2 points, we are going to explain, right? Logically explain the behavior of object, right? Under each region, under each scenario, right? Otherwise, this weird shape of the graph, these are strange shape, no? A different shape. This shape has come as a result of the experiment, right? That is why we are going to explain about this, because this is not like a typical graph, it's a special one, right? For any ductile material that we mentioned before, for metals, polythene, for any ductile material like such, the same shape is coming, right? So this is called, now you have to know this graph here onward, right? This is called the variation of Fe, right? Variation of Fe for a ductile material, right? So first take this down and have the exact shape from O to B, that is linear, and at B it deviates down and goes this way and comes to here, and point E is below D, point E is below D, and C is above B, and D is above B, E is below D, right? Copy down the exact one. Copy down the exact one. Exact one. Quickly. C and B at same level. That is what I just explained. C is above B. C is a little bit above B. C is above B. See, a little bit above B. I believe it drawn to IS. Yeah. So put to the main chat. Otherwise, when it goes to a separate chat box, so I won't see it. Right? Finished? And let's identify these points as well. A is called proportional limit. A is called proportional limit. Don't worry about these terms and words. We'll see everything in the coming part. B, elastic limit. Elastic limit. C, yield point. D, maximum stress. That is also called tensile stress. Maximum stress slash tensile stress. Take this down. And E, rupture point. Rupture point. Now let's see what's going to happen here, what's happening here, one by one. So let's see what's happening here and what causes this variation starting from here, right? Okay, take it down. Repeating again. Copy down the exact same shape, right? It should be the exact shape like this. Okay, let's move on. Let's move on. Now, we are going to explain these ones one by one, right? So write down as the first heading, proportional limit. First heading, proportional limit. Proportional limit. Within brackets, write down OA. Proportional limit OA. Write down proportional limit OA. Proportional limit OA. OA. Proportional limit. So in this diagram also I can mark it, right? OA is proportional limit now. So in the diagram also we can mark. Right? Let me draw this line from here to here, right? Then we can mark this from here to here as, right, proportional limit. Proportional limit. Proportional limit OA. Okay, listen now. Listen now. Okay. So before moving on, can someone tell me Hooke's law? Before moving on, can someone tell me Hooke's law? Quickly. Hooke's law. Before moving on, can someone tell me Hooke's law? Anyone? Hooke's law. Force and extension are proportional until the point of proportionality. Proportional. Correct. Good. Good. Right. So we know what Hooke's law is now. Right. We know what Hooke's law is. About the proportional limit. Right. About proportional limit. The reason is Hooke's law is applicable only up to proportional limit. Right. Hooke's law is applicable, which means for this ductile material follows Hooke's law up to its proportional limit. Right. The point of proportionality means proportional limit. Right. So that is what I wanted to link. That is what I want to link two limits. Right. So in Hooke's law we say, right, to the proportional limit. Right. Up to the proportional limit. That proportional limit and proportional limit here are same. Got the point? That proportional limit in Hooke's law and the proportional limit here are same. Right? Hooke's law is valid only up to this point. Only up to this point. Now we are going beyond. Okay, write down under proportional limit, write down. Hooke's law is valid. Hooke's law is valid. Hooke's law. Hooke's law is valid. Valid. Only up to proportional limit. Hooke's law is valid only up to proportional limit. Hooke's law is valid only up to proportional limit. Hooke's law is valid only up to proportional limit. Right, let's quickly recall what Hooke's law is. Okay, write down Hooke's law. Write it down, Hooke's law. F proportional to X. Right. So we can write this same as E because X and E are same, no extensions. Right. F proportional to E. Write it down. Write it down. This is called Hooke's law. And the equation comes from Hooke's law is F equals KE. Or you can also write this as F equals KX. Okay, write down Hooke's law in red. Write down Hooke's law is in red. Write down. Applied force is, write down, applied force is directly proportional. 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 Applied force is directly proportional to extension up to proportional limit. Directly proportional to extension up to proportional limit. Up to proportional limit. Up to proportional limit. Right. Let's move on. As the next heading, write down elastic limit. Next heading, write down elastic limit. Elastic limit, that is OB. Within brackets OB. Elastic limit. Now let me mark elastic limit on here itself again. Right? Elastic limit is all the way from here to B. Elastic limit is all the way from here to B. Like this. This one. Right? This is called elastic limit. Okay, now listen. Here onwards, for the ease of explanations, I'll be using a rubber band. Using a rubber band in the sense, as an example, I'll be using a rubber band. Let me check the rubber band is available. Right. Can you see this? You can see, right? So going to split this, right? Okay. Now this is the ductile material I'm going to use for the demonstrations here onwards, right? For the demonstrations here onwards. Listen now. Listen. Listen. It's better if I had a kind of a thicker one, right? But this is visible, right? Oh, yeah, it's visible. Ne? Okay, okay. Look at here. Look at here. Elastic limit is defined as this. Now these are rubber band. These are rubber band. It's a ductile material. It's a ductile material, right? Now when the force is applied, can you see it deforms? See? Can you see? It deforms, right? See? It deforms. Increasing shape, increasing length, it deforms. But when I remove this force, it is coming back to its initial length now. Is it clear? Now, when the force is applied, it extends. When the force is applied, it extends. But when the force is removed, it is coming back exactly to its initial length. Got the point? When the force is applied, it extends. But no worries, when this is removed, it comes back to its initial length. Right? So it's like nothing happened. It's like nothing happened. But when the force is applied, it was extending. But once the force is removed, it stays cool as nothing happened. See? That happens only within the elastic limit. Right? So therefore, elastic limit is defined as, listen, elastic limit is defined as, right, the limit where extension becomes zero when force becomes zero is called elastic. Right? So therefore, elastic doesn't mean only elastic. It should be able to come back as well. It should be able to return to its initial position as well. That is what we call elastic. Right? That is not only about stretching. That is not only about contracting. Right? Whatever happened, it should be able to come back to its initial length, initial shape. That is called elastic. Right? So that limit is called elastic limit. Right? I hope it's clear. Write down below, first point, under elastic limit, write down. Extension becomes zero. Extension becomes zero. Extension becomes zero. Extension becomes zero if applied force is 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 zero. Within brackets, F equals zero. Within brackets, F equals zero. Up to elastic limit only. 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 Within brackets again, write down E equals 0 when F equals 0. Write down this way. E equals 0 when F equals 0. E equals 0 when F equals 0. Right? Next point, write down. Which means, write down, which means the object comes back to, which means the object comes back to, which means the object comes back to, which means the object comes back to its initial length, its initial length. If force is removed, it comes back to its initial length. If force is removed, only within the elastic limit, only within the elastic limit. Only within the elastic limit. Only within the elastic limit. Right. Next point, use a red pen. Next point, for next point, use a red pen. For next point, use a red pen and write down Young's modulus. Young's modulus. Young's modulus Young's modulus Young's modulus is applicable. Young's modulus is applicable. Young's modulus is applicable only up to elastic limit. Young's modulus is applicable only up to elastic limit. Young's modulus is applicable only up to elastic limit. Okay, listen now. Look at here. Stop all your work and look at here. Look at here. Now, we know for this force, let me do this vertically. For this force, it extends and coming back. But if I keep increasing the force, see, if I keep increasing the force, see, if I keep increasing the force, right? When we keep increasing the force, after some point, right? Look at here. After some point, it retains some extension even if the force is removed, right? You also can try this out at home. See, now this is extended a little bit. I don't know it's visible to the video and the camera. Now initially it was something like this, but now it extends by a bit because I applied a force beyond elastic limit. That is what happened. According to this graph, I applied a force beyond the elastic limit. See, beyond the elastic limit. Then it retains some extension even if the force is removed. Got it? That is called a permanent set. That is called a permanent set. Once a permanent set is came to the material, we can't remove it, right? So if this limit is gone, which means it is gone. If it's gone, it's gone. Elastic limit එක පැන්නොත් ආයෙ එතෙන්ට ගන්න බෑ. It cannot be never taken back to the elastic limit again if elastic limit is exceeded. Got the point? If the elastic limit is exceeded, we can't take it back to initial length, right? We can't do anything at all, right? It's always going to retain a permanent set, right? That is called a permanent set. It is going to retain a permanent set. Going to retain a permanent set, right? Now, according to the graph, listen. According to the graph, look at the graph. According to the graph, when the force is applied beyond, right? When the force is applied beyond, now if I connect this kind of a point with this, see, if you extend this, can you see? Now from this, E is removed, is retained, right? And E is retained. But along this line, see, along this line up to B, it goes through center. Center means origin. Along this line, it goes through origin, which means when force is removed, it comes back. But here, even if the force is zero, see, even if the force is zero, when the graph is somewhere here, it retains an extension like this. That extension is called, let me draw this a little bit straight, right? That extension is called permanent set. That extension is called permanent set. Once the permanent set has come, that is permanent. The word says it is permanent. We can't remove it. That is called a permanent set, right? So this is how the permanent set is visible from the graph. Okay. Now, as the next point, write down. So try to grab these ideas properly because the core, I told you, the core of elasticity is here, right? The heart of elasticity is here. Core of elasticity is here in this graph, right? Okay. Write down next point. When force is continuously, next point, when force is continuously applied, beyond elastic limit, when force is continuously applied beyond elastic limit, when force is continuously applied beyond elastic limit, it retains a small extension. It retains a small extension it retains a small extension in the object. It retains a small extension in the object. Even when the force is removed. 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 Within brackets, write down. Within brackets, write down. Within brackets, write down. E is not equal to 0 when F equals 0. E is not equal to 0 when F equals 0. E is not equal to 0 when F equals 0. Right? To the same point, write down. This is called permanent set. This is called permanent set. So as the word says, permanent set is permanent. Permanent set is permanent. Right? If this limit is exceeded, which means there's no comeback at all. There's no comeback. Right? There's no comeback. Right? Equals 0 when F equals 0, and keep writing. This is called permanent set, and underline no highlight permanent set. Underline no highlight permanent set. Underline no highlight permanent set, and mark permanent set here on the graph. Mark permanent set here on the graph like this. Mark permanent set here on the graph like this. Mark it on the graph. Let's move on. Right. Listen. 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 Tell me if someone knows the opposite word of elastic. The opposite of elastic. Not inelastic. Not inelastic. Right? What is the opposite of elastic based on the materials? Based on materials. Anyone? Anyone knows? Rigid. Not really. Not really. What is the opposite of elastic? Now, elastic means ductile. No? Elastic is ductile. Right? Elastic in the sense it extends and comes back. Brittle. No. No, not brittle. That's a fun fact. That's why I asked. What is the opposite of elastic? Not inelastic. Malleable. No. Right. Let me break it down this way. Now, if this is an elastic material, right? Once the force is applied, it should deform. But once the force is removed, it should come back to its initial shape or initial length, right? Then the opposite should be, once the force is applied, it deforms, but it's never coming back. It's never coming back, right? There's a term for such material. As elastic material, there's a term for such material. Not inextensible, right? So they are almost similar words, I know, but that is not the technical jargon. That's right. Viscosity? No. Inductile? No. වචන හදනවද මන්ද? I don't know whether there's a word exists as inductile. I don't know. Moldable. No, not the technical term. It starts with P. Let me make it easier. Let me make your life easier. It starts with P. Opposite of elastic starts with P and ends with C. It's a fun fact. That's a word we are using day to day, right? That's a word we are using day to day. Yeah, it is plastic. It is plastic, right? We are using it day to day. But I don't think you have never heard about the definition of plastic. Definition of plastic is that, right? So even though we call that material as plastic, plastic is a property. It's a property as elastic. It's a feature. It's an attribute of the material, right? Elastic and plastic. Those two are the opposite words, right? Okay. Then next heading. Write down plastic flow. Next heading, plastic flow. Plastic flow. B to C. BC. Plastic flow. BC. Listen. Plastic flow. Look at the board. Plastic flow means something like this. Now, when we go deep down, right? Any material is made of layers, no? Any material is made of layers, right? Now, inside the material, it has its layers like this. Listen, it has its layers like this. Inside the material, right? So when a force is applied, listen, when a force is applied, what happens is, think about this in a micro level. When a force is applied, these are called layers. Layers of molecules. These are called layers of molecules. Listen. Right? When we continuously increase the force beyond B, listen, when we continuously increase the force beyond B, what happens is, these layers of molecules slides on each other in a micro level, right? They slide on each other. Now, when I do this, they slide on each other, right? So when they slide on each other, it creates heat, right? It generates heat, right? And due to that generated heat, not sometimes actually, most of the times, the material gets heated, right? Because of the generated heat, the material gets heated. And in addition to generation of heat, right, some points of the material are necking. Necking means getting thinner. Necking, right? Necking means, right? Necking means, right, some points of the material are getting thinner compared to other sides. Now, for the rubber band, right, if we look at a micro level, so likewise, some points of the rubber band will get thinner, like this, right? You can try this at home and see. And these thinner ones you can easily notice on rubber band, because it will be kind of faded in the color, right? In the rubber materials, right? It is getting necked, right? So the behavior of the object between B and C is called a plastic flow. Plastic means, right, I told you, plastic means that is the opposite of elastic. So when it starts the plastic flow, there's no comeback again. That is why it retains a permanent set, right? Right? But between B and C, it is not going to stay at the exact pace it was there once the force is removed. It comes back, but not to the initial length. It stops somewhere in between. That is because now after point B, plastic properties of the object starts to come into the play, right? Until point B, only elastic, that is 100% elastic, right? But after B, now plastic properties are also coming to the play, while elastic properties are still there, right? So therefore, with the elastic properties, they try to take it back, but with the plastic properties, it tries to keep it there without coming back. Then as a resultant, it stays somewhere in between, right? So that is called the plastic flow, right? Take this down. plastic flow. And this is what we call the plastic flow. Take this down quickly. Quickly. Plastic flow. This is a very interesting lesson, right? And an easy one. So try to grab everything from today itself. Then easily we can finish off all applications next day, and we can successfully wind this up, right? Okay, write down below. Don't write down nekin na. Make a only the plastic flow. Only the plastic flow. Only the plastic flow. Don't take this down. Only up to plastic flow. And write down this. Write down plastic flow. Write down below plastic flow. Sorry, write down below plastic flow. First point, plastic flow starts. Plastic flow starts. Plastic flow starts. Plastic flow starts right after. Plastic flow starts right after. Plastic flow starts right after elastic limit. Plastic flow starts right after elastic limit. When force is continuously applied. When force is continuously applied. When force is continuously applied beyond elastic limit. 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 Next point, write down the phenomenon of sliding. The phenomenon of sliding. The phenomenon of sliding slash dragging. The phenomenon of sliding slash dragging. The phenomenon of sliding slash dragging of layers of molecules. Of layers of molecules. Of layers of molecules. Of layers of molecules. Of layers of molecules on top of each other. On top of each other. On layers of molecules on top of each other. Layers of molecules on top of each other. On top of each other. On top of each other is called plastic flow. Is called plastic flow. Is called plastic flow. Underline no highlight 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 plastic flow. Next point, heat is also generated. Heat is also generated. Heat is also generated. Heat is also generated due to. Heat is also generated due to. Heat is also generated due to above relative motion. Due to above relative motion. Above relative motion among layers. Above relative motion among layers. Due to above relative motion among layers. Due to above relative motion among layers due to above relative motion among layers. Next point. Therefore, object starts heating and necking. Therefore, object starts heating and necking. Within brackets, getting thinner at random points. Getting thinner at random points. Getting thinner at random points. Right. So I think you can understand why the word necking is used. Huh? This is the neck, no? Getting thinner. That is called necking. Right? Same idea. Getting thinner. Make anything thin. I mean, from the whole body, when we come up from here, this is thin, and this part is again, it's kind of wider. So this is called neck. Same idea, necking. Right? So take this out. This is what we call necking. Right? That term is quite straightforward, no? Write down. Okay. In red, write down below. In red, using a red, write down below with an asterisk mark. Write down. Object shows. Write down. Object shows both elastic and plastic properties. Object shows both elastic and plastic properties. Between B and C. Right? So let me mark it on the graph as well. See? Then in this region, this is both. See? In this region, this is both elastic and plastic. It is both elastic and plastic. Right? It is both elastic and plastic. Right? So mark it on the graph as well. Right? Mark it on the graph. So how does necking restrict it from returning to its original length? Necking is not the one it restricts. That is the relative motion of layers. When layers are dragged here and there, it won't come back. That is because of the relative motion of layers. Layers move here and there like this. They behave differently, that's why. Okay, let's move on. Next heading, yield point. Yield point. That's a point. Huh? Yield point is a point. Yield point. Yield point within brackets C. That's a point. Yield point C. Okay, listen now. Yield point is something like this. Listen. So what's the meaning of the word yield? There are multiple meanings, right? So before explaining this, what are the meanings you know about the word yield? Yield. Yield. Any thoughts? Produce. Yeah, correct. What else? What else? Yield. Yield. No. There are multiple meanings for the word yield, right? So here the meaning of the word yield is like the margin, marginal, margin, something like that, right? Or the boundary, something like that. Okay, listen, this is the idea. This is the idea. Now I told you between B and C, both elastic and plastic properties are there. No? So when we keep increasing this force, when we keep increasing the force, right? When we keep increasing the force, right? There is a point, right? A certain point, right? Beyond that point, the material is not even start to coming back, right? That will stay there as it is, right? That will stay there as it is. Correct? Which means its elastic properties are totally gone now. Because if there is coming back, it should be due to elasticity. If there is not coming back, that is due to plasticity. Correct? And if it is not coming back at all, if it is not coming back at all, if this stay as it is, which means all elastic properties of the material are completely gone. All elastic properties of the material are completely gone, right? So that point where all the elastic properties are disappeared of the material is called the yield point. Yield point. That's the boundary of the elasticity. That's the boundary of the elasticity. Right? Write down first point. First point. When force is continuously applied, when force is continuously applied, when force is continuously applied beyond yield point, when force is continuously applied beyond yield point, when force is continuously applied, when force is continuously applied beyond yield point, when force is continuously applied beyond yield point, elastic properties of object, elastic properties of material, elastic properties of material will be completely disappeared, will be completely disappeared, will be completely disappeared. Right? Completely disappeared. Next point. The last point. Next point. The last point. The last point. Object shows. The last point object shows. The last point object shows elastic properties. The last point object shows elastic properties. Elastic properties is the last point object shows elastic properties is yield point. The last point object shows elastic properties is yield point. Is yield point. Right? Right? Next point. Next point. Therefore, the object is called, therefore, the object is called, therefore, the object is called a plastic object. The object is called a plastic object. The object is called a plastic object beyond yield point. Object is called a plastic object beyond yield point. Object is called a plastic object beyond yield point. Object is called a plastic object. The object is called a plastic object beyond yield point. underline or highlight plastic object. Underline or highlight plastic object. Right? Now, beyond the yield point, this is completely plastic, which means, see, after this point, right, this object is completely plastic. Completely plastic. It won't come back. Completely plastic. Completely plastic. Take it down in the sense, mark it on the graph itself, like this. Right? So as the next point, write down, only plastic properties retains. Next point, only plastic properties retain. Only plastic properties retain. Only plastic properties retain. Only plastic properties retain with the object. Only plastic properties retain with the object after. Only plastic properties retain with the object after yield point. Only plastic properties retain with the object after yield point. Only plastic properties retain with the object after yield point. Right. Listen. Now, since we have finished surface tension and viscosity already, I'll be allocating two S2A sessions for the question discussions on surface tension and viscosity as well, right? So in a coming week, I'll be allocating it, right? So far, what we have covered is linear motion, projectile motion, vectors, and equilibrium, no? Right? So in a coming day, I'll be allocating 2 days actually from S2A sessions for past paper discussions here in surface tension and viscosity, right? These already completed parts, right? Okay, mark it here as plastic. Let's move on. As an next heading, write down maximum stress / tensile stress. Next point, next heading, maximum stress / tensile stress. Maximum stress / tensile stress, right? D within brackets D. Okay, listen. So this is also very much straightforward with the term itself. Maximum stress means, right, that is the point where the object will be withstanding for the maximum possible stress or the maximum possible force the material can withstand for, right? Maximum of all, right? So there's a particular point on the graph, right, where the object can withstand for the maximum force that we have applied, for the maximum force. That is called the maximum stress, right? Simple as that. Write down below. This is the point where, write down, this is the point where the object withstands to the maximum possible force. Withstands for the maximum possible force. Maximum possible force to the maximum possible force that can be borne by the material. 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 Right. Next one, rupture point. Next, rupture point. rupture point E, rupture point E, rupture point E, right? Right. So what is rupturing? Rupture means rupture, fracture, break, everything are same. Rupturing means it's breaking, right? So after the maximum point, if we increase this force even beyond the maximum force, right? Even beyond the maximum force, now the object is already necked, right? The object is already necked, right? Some places, some points of the object is already necked. So therefore, this happens at a neck point, right? Because they are already neck, no, their strength is less, right? So this happens at a neck point. When we increase this force further beyond the maximum force, right, it is going to break the material, it is going to rupture the material from a neck point, right? So therefore, when it's ruptured, the force it need to be applied is less than the maximum force, right? So at the point it is ruptured, the applied force is less than the maximum because it is going to rupture from a neck point, right? Because it is already neck, then with the small force, right? Small force compared to the maximum force, it's getting ruptured, right? Then after that point, the material is no more. Material is no more, that is ruptured. The material is ruptured and no more. And that is the ultimate end of this curve. That is the ultimate end of this curve once the material is broken, right? Okay, write down first point under rupture point. First point, write down. This is the point where 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 the object is broken. This is the point where the object is broken. This is the point where the object is broken. This is the point where the object is broken. This is the point where the object is broken. Within brackets, ruptured. This is the point where the object is broken. Within brackets, ruptured. Within brackets, ruptured. Second point, mostly this happens, mostly this happens at a neck point. 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 Right? Mention the other point in red. Mention the other point in red. Mention the other point in red. Therefore, required force at rupture point. Therefore, required force at rupture point. Therefore, required force at rupture point. Required force at rupture point. Required force at rupture point is a bit lesser than maximum stress. 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 Okay, listen now. So that is all about this behavior, right? So when it comes to our questions, this is the core area we have here in elasticity when it comes to our questions, right? So that's all about this behavior from O to E, right? Now raise your questions if anything, and raise your hand or at least put the thumbs up if it is all clear up to this point. Quickly. There are some more things to do. Quickly. So before I erase, tell me. Good. Others, what about others? Okay, others. All right, let's move on. Right, listen. Now, without giving FE, right, the standard graph we have is FE. So, without giving FE, if the graph is product between, right, stress and strain, F over A, right, and E over L, stress and strain, right, still the graph is same. Still the graph is same. Still the graph would be same, right? So even though it is plot between these two, still the graph is same. Okay, write down below as a point. Write down below as a point. Write down. If the graph is, write down. If the graph is plot between, if the graph is plot between, if the graph is plot between a stress and strain, if the graph is plot between stress and strain, the shape remains exactly same. 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 And take it down as well. Take this down as well. This is stress F over A. F over A. Stress and strain. Right, take it down. Okay, let's move on to the next part quickly. Write down variation between tensile force and extension. Variation between tensile force and extension. Variation between tensile force and extension. Tensile force and extension. Variation between tensile force and extension. Tensile force and extension of a brittle material, of a brittle material, of a brittle material, of a brittle material. Okay, look at here. This is also an experimental result, right? FNE of a brittle material. Now, for brittles also, it has a certain, right, very small, very small. It has a certain, what we call the proportional limit and an elastic limit, but they are very small. And just after the elastic limit, it ruptured. Just after the elastic limit, it ruptured, right? Because they can't undergo plastic flow. Plastic flow is where the molecule layers are dragging, are sliding on each other. Brittle materials can't undergo that sliding plastic flow. So therefore, soon after the point of the limit of elasticity, it breaks, right? And yet the elastic limits are very much small, very small, right? Okay, take it down. And only 3 points are here. There are only 3 points. They are also very small, right? A, proportional limit as usual, proportional limit, and B, elastic limit we have labeled before, and E, rupture point. Let me explain again. When it comes to brittle material, naturally there are elastic limits and proportional limits are very much small, right? But they have a limit, but very small, negligible one. They have a limit, but very small. Now, for the graph, in the graph, for you to see, I have draw magnified one. I have drawn a magnified one. Otherwise, their limits are very small, right? And soon after the elastic limit is exceeded, they can't undergo plastic flow because they don't withstand for this relative motion of a layers. No, right? They don't have a plastic flow, right? They don't have a plastic flow. Then ultimately, I mean, ultimately in the sense, soon after E, soon after B, what happens is it's getting ruptured. It is getting ruptured, right? Now, for a material like glass, right? So up to some extent, it is withstanding for the applied force, right? For some extent, but once that force is exceeded, it is breaking, right? Write down proportional limit, elastic limit, and rupture point. Now compare these graphs now with the ductile and brittle. Then we can easily understand with the differences. E is higher than B. Yeah. Higher than B. It's same as before. Lay down. Right. So this is all about the ductile and brittle behaviors. Right. This is all about the ductile and brittle behaviors. Right. And next as the next topic, write down malleability. Malleability. I think that you know what is malleability. What is malleability? You know this. What is malleability? Now we are going to recall again. What is malleability? Anyone? Malleability. Malleable or malleability. What does that mean? What does that mean? Ability to convert to sheets. Yeah. Again, a little bit different idea from the exact one, right? A little bit different idea from the exact ones. That is also same as the ductile one, right? Yeah, it's correct. I mean, the idea is correct, but not the exact one. Ability to convert to sheets, correct. So I think you all know that idea from O levels. Ability to convert to sheets, right? Now, the ability to convert to sheets means it should be able to hammer, no? Right? Now, if I need to convert this, say, if I need to convert this to a sheet, right? If I need to convert this to a sheet, we have to hammer this. We have to hammer this. Once this is hammered, right, this thickness decreases, right? This thickness decreases like throughout the process, and we can get a sheet. We can get a thin layer that is called a sheet. Is that clear? Now, if I need to convert this to a sheet, we have to hammer this, right? We have to hammer this. Therefore, malleability is defined as the ability to being hammered. Malleability is defined as the ability of an object to being hammered, right? A result of hammering is making sheets, right? Write down below. Write down below. Malleability is the property. Write down. Malleability is the property. Malleability is the property. Malleability is the property of an object. Malleability is the property of an object to determine object to determine limits to which property to determine limits to which to determine limits to which the object can be hammered. The object can be hammered. Limits to which the object can be hammered. The object can be hammered. Right. Okay. Now, because of these extensions, changing shapes and everything, right? Acting forces and everything, this also stores an energy in the material, right? It stores an energy in the material. That is called strain energy or elastic potential energy, right? That is called strain energy or elastic potential energy, right? Write on the next line as strain energy, strain energy slash elastic potential energy, right? Strain energy slash elastic potential energy, right? So keep that heading written. I'll be continuing the discussion after this next day, and this is the only part remaining here, and 95% of theories are covered, right? 95% of theories are covered, and from energy there is one more equation to be discussed. Right? It will take around like 15-20 more minutes. That's it, right? Strain energy and elastic potential energy. So almost all theories are covered, and our main plan next day is, right, all the types of applications here in elasticity, right? So next day will be a full day with applications of elasticity, right? A full day of applications of elasticity, right? And listen, and the week after next week we'll be starting the new unit, matter and radiation, and I'll be allocating us to a discussion for the discussion of the covered lessons. Plus, sooner you are going to have the optical instrument seminar, right? The optical instrument seminar as a night seminar, right? Sooner I'll inform all the dates and times through channels and groups, right? So any other questions? Any other thing to clarify? Any other thing to know? Anything to know? So how about elasticity so far? How is it? How was the lesson? All lessons here in properties of matter are very interesting ones. They are very interesting. Okay, how about it? Are you all clear? How about it? Are you all clear? So ask if anything. Now it doesn't matter even if you put a private message, right? Now I'm at the laptop now. So it doesn't matter even if it's a private thing, you can put it private, that's fine. So ask if there's anything. Will it go until midnight like practical seminar? Yeah, around midnight, but not as long as a practical seminar. It will be something for like 4 to 5 hours, something like that. Say 5 hours. 4 Madi, 4 Madi, 4 is not enough. Around 5 hours, something like that. Any other questions? All good? Okay then. Then all clear, right? Good. Okay then. Then if you know any questions we'll wind up and by the next day, after the upon the completion of elasticity with the applications, right, we'll be completing the first unit in our previous class, properties of matter, right? All right then, and reminding you again, you are 26 weeks ahead of the exam. Right now, this week is also gone. It is almost gone, which means we are only 25 weeks ahead of the exam. Just 25 weeks, right? Just 25 weeks ahead of the exam. So work hard, right? Give your fullest. Give your fullest to this these days. Give your fullest. Give your maximum to these days, right? And do that sacrifice for these 25 weeks. Then you can get the results, right? Benefits, advantages, results of the sacrifices you do here for a lifetime, right? For a long lifetime. All right then. So with that, I'll wind up. See you in the next class, right? No questions, no? Right, okay. See you in the next class. Good night and goodbye. See you.